Do you remember the axioms of set theory? For the basic set manipulation, we have the axiom of separation, which produces a subset of a given set given by a rule, and the axiom of extensionality, guaranteeing that a set is uniquely determined by its elements. If we have two sets with identical elements, they must be identical as well. The axioms of existence and pairing are capable of creating small sets with 0, 1, or 2 elements. Further axioms can help with creating large sets. There is the axiom of infinity, providing us the set with all the natural numbers to start with. We continue with the axiom of power set and build bigger and bigger sets. After that, we use the axiom of replacement to pack all the results into a single set, and we finish it with the axiom of union to put all the elements into a single set bigger than all the previous sets. Then there are two a bit more advanced axioms. The axiom of regularity guarantees that there are no weird sets. This axiom is not too important and we can build the entire set theory without it. And then there is the axiom of choice, which will be covered in this video. It can be phrased as follows. For any set of non-empty disjoint sets, we can take exactly one element from each of these sets and pack them into a new set. A vague but fitting description of the axiom is: we can make infinitely many unorganized choices at once. Why infinitely many and why unorganized? There are no such conditions in the formal axiom. We just don't need the axiom in the opposite case. For instance, assume that we have just finitely many of the sets. We can take one element from one of them. We don't need any axiom for taking an element from a non-empty set. That's the definition of a non-empty set, that we can find an element in it. We also don't need the axiom of choice to pack the elements into a singleton set. The axiom of pairing can do that. And if we want to pack a finite number of such elements, we use unions of pairs. We have discussed this in the 9th chapter about axioms. Once we need an infinite number of choices, gradual taking of unions of pairs won't be enough. So we need a mass operation that can construct an infinite set directly. The axiom of replacement can do this. It gets a rule, in our case say replace every set with its lightest element, and it will transform our colorful set of sets into the set of its representatives. Well, the lightness of an element doesn't sound as a very rigorous definition, but we could think of something more formal in specific cases. However, the axiom of replacement needs a clear rule. The axiom of replacement cannot just transform a set with its arbitrary element. This is the work for the axiom of choice. Just to be clear, the axiom of choice doesn't guarantee its output to be random in any way, say, from the perspective of the theory of probability. The adjective unorganized in the description doesn't mean that the result is really going to be random. It only states that we can use the axiom of choice even when there is no organized way to do it. Now you should be asking, well, but how can it happen that there is no organized way? We are going to look at two examples, one presented as a fairy tale and the other one from real mathematics. Prisoners guessing heads and an unmeasurable set. There are many problems with prisoners having heads on their heads. Most of the problems consider a finite number of prisoners, and the prisoners can usually get some information based on the behavior of others. Our problem differs in these aspects, but otherwise, the story is quite standard. A tyrant king has jailed an infinite number of people, and now he wants to execute them. Just before the execution, he came up with a game for them to stress them out a bit and make them feel that it is their fault. In the morning, before the execution, he is going to put a yellow or blue hat on each of them, and he lines them up so that every prisoner can see the infinite number of heads in front of him, and he doesn't see the finite number of heads behind him. He also doesn't see his own head, of course. Every prisoner knows his position in the line. Now, all at once, all the prisoners guess their heads. In case of only a finite number of mistakes, the king will let all of them go free. Whenever there will be an infinite number of mistakes, the king will execute all the prisoners. Ha 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 ha. That feels pretty hopeless, don't you think? When they have no clue about their own heads, every prisoner has about 50-50 chance of getting it right. So on average, every second prisoner will make a mistake. But since this test is going to take place tomorrow, they have some time to agree on a strategy. Some strategies work in very special cases. For example, if you see just blue heads in front of you, guess blue. Maybe you will be wrong, but all the prisoners in front of you will guess the right color. With this strategy, there will be only a finite number of mistakes. If we want a strategy working in every case, we need to be a bit more general. Let's draw any distribution of heads as the appropriate sequence of colors in a similar way as we were drawing the ordinal numbers. Let's consider the set of all such sequences. There is an uncountable number of them, although we have drawn just 4 examples here. We will split the sequences in our set into groups. We put 2 sequences into the same group if they coincide from a certain point on. In other words, any 2 sequences in one group differ in a finite number of positions. So we convert the set of all sequences into a set of disjoint groups. By the way, there is still an uncountable number of such groups, although we draw just 4 examples. One such example are the sequences with an arbitrary beginning followed by only blue heads. Another such example are the sequences with arbitrary beginning followed by blue heads on the even positions and yellow heads on the odd positions. We simply care only about the tails of the sequences. The trick is that although a prisoner doesn't see the entire sequence, he can recognize which group the true sequence belongs to, simply because the finite number of positions he doesn't see cannot influence the group. Even though the prisoners cannot see all the heads and they cannot talk to each other, they all share the knowledge about the right group. No matter which sequence we take out of the group, it will coincide with the true sequence from some point on, simply because every 2 sequences in our group do. So it is enough for every prisoner to guess the appropriate color, and they will make only a finite number of mistakes. But how can they all pick the same representative when they cannot talk to each other during the test? Well, they have to agree on it beforehand. Before the test, they have to consider every group of sequences having finite differences and agree on a single representative. Unfortunately, there is no general rule to select the representative. So, what are we going to do? Surprise, surprise, we use the axiom of choice. The axiom of choice selects one representative out of each group and packs them into a set. The prisoners will agree on this set of representatives as a part of their strategy. Well, it feels a bit like cheating to have an uncountable set of representatives as a part of the strategy, but in a world with infinitely many prisoners, they can memorize an uncountable set of sequences. What can be so hard about it, right? Having this strategy, all the prisoners will notice the right group of sequences. They all realize which representative from this group they agreed on, and as a result, only finitely many prisoners will be wrong. So the axiom of choice saved infinitely many human lives, and all the prisoners returned to their families and lived happily ever after. If you would like to learn a bit more about this story, I can refer you to a video by Mathologer, Death by Infinity Puzzles and the Axiom of Choice. And now, let's take a look at another example closer to real mathematics. In mathematics, we often assign an area to a geometrical object. The area of a triangle is half the base times the altitude, the area of a circle is pi r squared. Once, mathematicians thought that some area can be assigned to any set, no matter how crazy it is. When you try to generalize area for arbitrary sets, it is reasonable to start with the real line instead of the plane. Such an area on the real line is called a measure. Well, a measure can also mean area or volume in general, but we will use just the one-dimensional measure. So for example, the measure of an interval is equal to its length. The measure of the union of two disjoint intervals is the sum of their lengths, and so on. The measure should satisfy the following properties. First, if we add new points to the set, its measure should not decrease. Second, if we shift a set by a real number to the right or left, its measure should remain the same. And third, the measure shouldn't change even if we split the set into countably many pieces. We shift each of them independently so that they remain disjoint and merge them back together. Unfortunately, it is not possible to assign some measure to every set and fulfill all of these conditions. The axiom of choice helps us to construct a subset of the interval 0, 2, so its measure shouldn't exceed 2, yet it is possible to split the set into countably many parts, shift these parts, and use them to fill the entire real line, so its measure should be infinite. Let's go. This time we split all the real numbers into groups modulo q. It means that we put two real numbers into one group if and only if they differ by a rational number. A typical example of such a group is the set of all the rational numbers. In general, we construct such a group by taking a fixed real number, say the square root of 2, and shift all the rational numbers by it. Every such group has some elements in the interval 0, 1. Using the axiom of choice, we choose one such number from each of these groups. The resulting set of representatives will be called R. So, whenever we take two elements of R and shift them by a rational number, we never hit the same real number because both elements come from different groups. There is also another way to look at it. Whenever we take two copies of R and shift both by different rational numbers, the two copies must end up being disjoint, simply because no number from the first copy can hit any number from the other copy. To finish the measure paradox, we use a well-known fact about cardinalities. The cardinality of the rational numbers between 0 and 1 is Aleph 0. It is the same as the cardinality of all the rational numbers. The paradox is now formed by Aleph 0 of copies of R. There are two ways how to shift the Aleph 0 copies of R. If we shift them only by rational numbers between 0 and 1, we obtain a subset of the interval 0, 2, so the measure of such a set should equal at most 2. However, the copies of R were not overlapping, so we can split this set back to the Aleph 0 copies of R and shift them by all the rational numbers. Suddenly, we cover all the real numbers, so if we shift them this way, the measure should be infinity, although it was 2 or less before. Therefore, the set R provides a counterexample to the requirements for the measure we have set up before. Now, let's make sure that we have covered all the real numbers. Whenever we take a real number x, this number is in one of the groups. This group has a representative in the set R. If we shift this representative by an appropriate rational number, we cover x. So x was covered by R shifted by all the rational numbers. Whenever a problem pops up, it is natural to search for something to blame. The condition about splitting the set into countably many parts was quite artificial, and a significant role in the axiom was played by counterintuitive properties of Aleph 0. Perhaps the measure could work without this requirement. Well, not really. There is a similar, a bit more complicated three-dimensional example where you decompose a ball into finitely many parts, shift them around and create two new balls identical to the original one. This construction is called the Banach-Tarski paradox. There is a good video about it by Vsauce. So, should we blame the axiom of choice? Maybe, or rather our intuitive notion of a volume just cannot work for arbitrary sets. The axiom of choice was quite controversial in the past, also based on the examples we have seen. Today it is mostly accepted as one of the basic axioms. One of the reasons for its acceptance is that logicians managed to prove that the axiom of choice as well as continuum hypothesis cannot be proven nor disproven using the other axioms. This is not sufficient as a reason. the continuum hypothesis isn't automatically considered valid, but intuitively the axiom of choice should really hold and is also necessary for other innocent-looking propositions. We will see such a proposition in the next chapter. In particular, we are going to prove that every non-empty set without the first element contains an infinite decreasing sequence. See you then!